Yes, exactly.
Okay, so hello everyone, bonjour tout le monde. Thank you for joining us today and merci de nous joindre aujourd'hui. Our event is entitled Machine Learning, an Introduction to Data Science, apprentissage automatique, une introduction au monde des sciences des données. So I will start first by introducing Professor John Hall. So Professor John Hall is Maple Financial Professor of Derivatives and Risk Management at the Joseph L. Rotman School of Management, University of Toronto. He was with Adam White, one of the winners of the Nicolor Research Competition for his work on the whole white interest rate model, which is widely used by practitioners. Il a été avec Alain White, l'un des lauréats du concours de recherche Nicolor, pour ses travaux sur le modèle de taux d'intérêt whole white, largement utilisé par les praticiens. In 1999, he was voted Financial Engineer of the Year by the International Association of Financial Engineers. He has written 4 books. Il a écrit 4 livres: Risk Management and Financial Institution, Options, Futures, and Other Derivatives, Fundamentals of Futures and Optics Markets, and Machine Learning in Business, an Introduction to the World of Data Science. The books have been translated in many languages. Ils ont été traduits dans de nombreuses langues, and are widely used by practicing managers as well as in the classroom. So Dr. Hall is an academic director of FinHub, Rotman's Financial Innovation Lab, and co-director of Rotman's Master of Finance and Master of Financial Risk Management programs. In addition to the University of Toronto, Dr. Hall has taught at York University, University of British Columbia, New York University, Cranfield University, and London Business School. So our event will be recorded, and it will be uploaded later in our YouTube channel. If you feel like watching it again, or you want to share it with your friends who couldn't make it today, feel free to do that. We will be sharing on social media once it's uploaded. Thank you, Professor Hall, for coming today and accepting our invitation. So yeah, I will leave the word to you now, and let's start the event.
Well, thank you very much, Emin, and thank you for inviting me to this event. Let me start by sharing my screen. And here we go. So the title of this presentation, Machine Learning in Business, an Introduction to the World of Data Science. It's actually a little bit of a new venture for me to work in the machine learning area. What I'm probably best known for is my work in derivatives and risk management. But about 5 years ago, I realized, along with a lot of other people, of course, that machine learning was just becoming more and more important to students in business. And there were so many interesting research ideas in machine learning. So I moved my interest to machine learning. And one of the results of that, let me just make sure I've got this right. One of the results of that was I wrote a book, actually a 4th book, which Emin mentioned, which has got the same title as this course or this session, Machine Learning in Business, an Introduction to the World of Data Science. And, you know, my teaching and research at Rotman has switched to machine learning in the last few years. And this presentation will be based on, you know, some of the material in the book. Obviously, there'll be a lot more material in the book than I'm able to present in 2 hours. If you're interested in sort of, you know, examining what else is in the book, what the book covers, you can go to my website, which is listed there. I think the key point here is that we're all going to have to learn about machine learning over the next few years to survive in business. It's sort of permeating all aspects of business. And the analogy that I use with students is the following one, that we teach you accounting. We don't teach you accounting to become accountants, but we teach you accounting so that you can interact with accountants, understand the language of accountants, understand the sort of thing that accountants do, and so on. It's the same with machine learning. Most of the people who take my courses are not going to become data scientists, but they are going to, for sure, be interacting with data scientists on various machine learning projects. And, you know, my courses at Rotman are training them to do that. And my book is a book that's been written with that in mind. It's a book that's been written to persuade people or to enable people, I should say, to work productively with data scientists, but not to enable them to become data scientists. And when I started teaching this material, I found it very difficult to find a book which was in that category. Most of the books that have been written are, of course, for computer scientists. So let me start the presentation. And there's actually going to be 3 parts to the presentation: an introduction to machine learning, neural networks, and reinforcement learning. We're going to divide the time roughly equally between these 3. If you want to ask questions, feel free to do so at any time. I may, you can either put the questions in the chat or, put your hand up indicating that you want to ask a question with your mic switched on. I may miss it because obviously I'm focusing on the slides and what I'm saying, but Emil and the other administrators should feel free to interrupt me if there's a question.
We'll make sure of that.
Okay.
Yeah.
So let's get started. Introduction to machine learning. I probably don't need this slide with this group, but let me, go through it anyway. What is machine learning? It's a branch of artificial intelligence, and the idea is a pretty simple one, actually. The idea is that we give a computer program access to lots and lots of data, far more data than we're used to dealing with in statistics and so on, and let it learn about the relationships between variables and make predictions. Okay, so let it learn from lots and lots of data. That's where the word learning comes from. And I'm sure you're all aware that there's been a lot more in the news about machine learning in the last few years than there were before. Actually, the idea, the techniques of machine learning date back a long way. They date back to the 1950s, but I think the reason why we've heard so much about machine learning in the last few years is just because computer speeds and data storage costs and so on have really caught up. These techniques of machine learning, which have been around for quite some time, they weren't really viable until recently because computers just weren't fast enough. And so that's, and of course, computers are getting faster all the time. So I think it's important to distinguish between machine learning and automation, because machine learning is more than automation. We've been living with automation for quite a long time now. Computers are used for all sorts of, roles of automating business decisions, payroll, sending out invoices, and so on. What this is usually referred to as the third industrial revolution. I mean, we've all had to get used to working with computers, using computer programs that have been written by other people, and all of that sort of thing. So to say, that's the third industrial revolution, and we could call it automation or digitization. Machine learning is central to the fourth industrial revolution, which is where computers are used to create intelligence. And I think we're living in the birth of the fourth industrial revolution now. And what I'd like to do is, this is an application of machine learning that I use with the students, but I'd like to use it myself. Okay, you can hear me? Good. I hope I haven't been I hope I haven't been muted for too long. Okay, where were we? So talking about the third and fourth industrial revolution, and let me sort of try and illustrate the difference between that. One of the big successes of machine learning has been automating loan decisions, credit decisions, as they would be called. You know, you apply for a loan, does it get accepted or rejected? Almost certainly, if you do that, the decision is going to be made by a machine learning algorithm these days. It's not going to be, you know, it's not going to be made by a human being, at least in the first instance. So let's think about, you know, how do we automate loan decisions? If we're a bank, you know, how do we automate loan decisions? I've got 3 different alternatives here, which kind of illustrate what I'm trying to talk about. The first is, let's suppose that we know how loan officers make decisions. You know, there's some handbook they use and we know the rules. Then it would be fairly straightforward to program a computer to implement those rules. Okay, and that would be the 3rd industrial revolution. We'd just be automating something which is done in a fairly standard way by human beings. But it's more likely that we're in the 2nd category, where we don't know the rules that are used, but we'd just like to get a computer to, you know, use those rules, whatever they are, that are currently being used, but we'd like to learn what the rules are first of all. So we could use machine learning for that. And how would we do that? We'd give the algorithm lots of information on past lending decisions, you know, the characteristics of the borrowers, which are called features in machine learning. So, you know, what's their credit score? What's their income level? How long have they lived in their present house? All of those features which might be used by loan officers, we'd give that to the algorithm, and we'd also tell the algorithm what the decision the loan officer made. So this is the historical data, and the algorithm would work out, well, what are the rules that the loan officer is using? And then once we know the rules, we can automate them. So the role for machine learning there is learning the rules that the human beings are using that you know, are not written down anywhere. And then there's the 3rd application of machine learning, which is what you know, most financial institutions use, which is to go one step further and saying, can we improve on the rules that the lending officers are using? So let's give the algorithm data on past loan applications and see how they worked out, you know, or see how the ones that were accepted. Anyway, this is one of the problems, of course. You don't know how the loan applications that you turned down, you don't know how they would have worked out. But the ones that you accepted, you know whether you got repaid or there was a default. And so you would give the algorithm information again about the loan applicants, but you would also give the algorithm information about whether, you know, whether the loan proved to be good or whether it defaulted. And then the algorithm would say, well, maybe we can improve on our decision making a little bit by, you know, slightly changing our criteria. Okay. So, you know, as I say, the first of these 3 bullet points is just the 3rd industrial revolution. The 2nd and the 3rd are 2 different applications of the 4th industrial revolution, which are commonly used, you know, by financial institutions. Okay. So what I want to do in terms of, as I say, introducing machine learning is to sort of contrast it with traditional statistics, because I'm sure everybody who's listening to my presentation has taken a course in statistics at some time or another. And, you know, what did you learn on that course in statistics? You know, well, mean, standard deviations, probability distributions, significance tests, confidence intervals, linear regression. I'm sure all of those topics are things that you're familiar with from the statistics courses that you've taken. But you could say that machine learning is just the new world of statistics. We've now got huge data sets, fantastic improvements in computer processing speeds, data storage costs. And as I said earlier, those machine learning tools that have been around for quite some time are now feasible. So, you know, we can do things that we couldn't do before. In particular, you know, the natural assumption, the natural thing we tend to do in statistics is to assume a linear model and use linear regression. And the nice thing about using a linear model is that, you know, once you've made the assumption that the relationship between the dependent and the independent variables is linear, you don't need that much data. Okay, 50, 100 data items will do it in terms of, you know, estimating a linear model. But when we've got lots more data, we don't have to assume the model is linear, and we're going to see that later on in this presentation. So we can develop nonlinear prediction models, and we can find patterns in the data that were just not possible before because we didn't, you know, have the same volume of data. One thing that, of course, in any field is important is learning the terminology used by the field. I was drawing the analogy with accounting earlier. You have to, obviously, accountants have a lot of, you know, accounts receivable, accounts payable, you know, this and that they use. And of course, machine learning has a lot of terminology. When I first got into machine learning, I found this very frustrating in point of fact, because the sort of terminology, I mean, I was sort of trained in statistics, same as you. And what I found was that pretty much every single word that machine learning people use for a particular thing is different from the corresponding word in statistics. You know, if there was a corresponding word in statistics, it's just not used. So here's, you know, here's some examples. I mean, features. What are features? You know, features are the things, you know, if you go back to that lending decision, the features are, you know, what's the credit score, what's the income level, you know, the characteristics of whatever it is you're looking at, you know, and what statisticians would call independent variables, you know, machine learning people call features, and then labels are the values of the thing you're trying to predict, activation functions, targets, you know, and so on. I mean, I'm not going to define all these variables now, but as we go through, you know, I'll try and indicate some of the terminology that you have to get used to as you get into this sort of area. So here's a slide that contrasts. I mean, I've said there's a lot of parallels between statistics and machine learning, but there is an important difference. In statistics, the way, you know, if you do statistics properly, what you do is you sit in an armchair and develop a hypothesis. You don't look at any data. You sit in an armchair, you develop a hypothesis. Once you've refined your hypothesis, you go out and you collect data and you test the hypothesis. I mean, that's the standard way of, you know, doing statistics. Machine learning, the way you do things in machine learning is quite different. The first thing you do is you go out and you collect the data, hopefully lots of it. And then you try different models and you choose between the different models, and you find patterns or develop a predictive tool. So, you know, machine learning is all about, so, you know, we've got all this data, let's try and find a model that explains the data that we can use on new data to find patterns or develop a predictive tool. Okay, so it's a different process. There's no hypothesis in machine learning. Whereas in statistics, you know, the hypothesis is sacrosanct. So it's, you know, different process, if you like. So let's talk a little bit about the types of machine learning out there. And again, you know, if I was thinking of terminology to describe these things, I wouldn't choose the terminology that's here. But this is the terminology that, you know, computer scientists or machine learning people have come up with. So we've got to live with it. So unsupervised learning. What's unsupervised learning? Unsupervised learning is just finding patterns in your data. In the time that I've got available today, I won't be talking about unsupervised learning at all, but you know, a popular use of unsupervised learning is, you know, you've got lots of customers, you just want to understand your customers better. You're not, you know, so basically you tell the algorithm about a lot of features of your customers, and the algorithm will cluster your customers. It'll say, you know, this is one cluster of customers, this is another cluster of customers. And it's been shown that actually machine learning algorithms are better at clustering customers than, you know, than human beings. Okay, but there's no prediction going on. You're just trying to understand your data better. Supervised learning is where you're trying to predict something. Now, there's two sorts of supervised learning. One is where you're trying to predict a numerical value. You know, an example I use with students is predicting the prices of houses. Okay, so how do you know, you've got all the features of the house, you know, the square footage, number of bedrooms, lot size, and so on. And you try and predict the price of the house from its many features. Or there's classification, and classification, you know, about an example of classification would be the lending decision that we talked about earlier, because what you're trying to do in classification is to classify the loans into two groups, those where you actually want to make the loan and those where you don't, okay? Or, you know, another example could be trying to identify fraudulent transactions. So you've got all the features of the transactions and you're trying to classify them as fraudulent or not fraudulent. So as I say, two main types of supervised learning, predicting a numerical value or classification. Why is it called supervised learning and unsupervised learning? You know, it's pretty opaque, but, you know, I guess the thinking is that if we're trying to predict something or classify something, then we've got to supervise what's going on with the learning to meet that objective. Okay, so that's where the word supervised comes. You know, we've got to indicate to the algorithm that this is what we want it to do. In unsupervised learning, you're just, you know, looking for patterns, and so you don't have to supervise it as much. I mean, I find that, you know, as I say, fairly strange terminology, but this is the terminology that's used. Then there's semi-supervised learning, which is halfway between the two. So it's this is where you've got lots of data, but you're trying to predict something like the price of a house, or, you know, classify lending decisions or whatever. You've only got labels, as they're called, for part of the data. Okay, so you're kind of in an unsupervised learning environment because you know, in unsupervised learning, you haven't got any labels because you're not trying to predict something. Okay, so but you can imagine what we'd be talking about with semi-supervised learning might be, you know, we're trying to predict the prices of houses. We've got lots of information on different houses, but only part of that data actually tells us what the price of the house is. Okay, so we say only part of the data is labeled. It's, you may say, well, what's the use of the rest of the data? You know, and it turns out that, you know, you shouldn't throw away the rest of the data. It can be, you know, it can be useful. You know, an example that I use in the book here is, you know, let's suppose somebody from another planet comes down to Earth and you know, they're walking around a neighborhood, looks a little bit like a human being, walking around a neighborhood, but they don't know anything about what human beings do. And they observe some pets, some animals, and some of them are cats and some of them are dogs. But of course, you know, this person doesn't know anything about cats and dogs. So, but he could sort of classify the animals. He could use unsupervised learning to say there seem to be two categories of animals that I'm observing. Well, doesn't know to call them cats and dogs, but there's, you know, there's two clusters of animals. And then this, you know, then this person sort of actually meets somebody, and that person says, you know, that animal over there, that's what we call a cat. And this other animal over there, that's what we call a dog. And so then say, well, that explains a lot. You know, I had these clusters of animals. I now know that, you know, one cluster is, you know, because that cluster is, if I just identify something that I would have put in that cluster as a cat and another one as a dog. And so you can see how you can extrapolate. And it is useful to have, you know, data that is unlabeled. So that's maybe a stupid example, but it kind of illustrates the sort of way in which you can handle situations where only part of the data is labeled. And you know, you can come up with more sophisticated examples involving predicting house prices or something like that. Final bullet point here is reinforcement learning. And this is where you're not just taking one decision or trying to predict one thing. What you're doing is taking a whole sequence of decisions, you know, in a changing environment, potentially. And we'll be talking about this later on. So, you know, as I say, you know, and basically you've got to come up with some sort of a decision strategy for, you know, the series of decisions that you've got to take. Okay. Now, one thing that, you know, I want to stress when in talking about, you know, machine learning is what you know, what might be termed good practice. You know, remember I mentioned that what you do in machine learning is you collect data, you try out different models, and you choose your final model. So what you actually do is you hopefully have lots of data, and you divide the data into three sets. The training set, the training set, the validation set, and the test set. Okay. Typically, you might put 60% of your data in the training set, 20% in the validation set, and 20% in the test set. And it's very important that you do this, because what you're going to be doing is trying out different models, and you may come across a model that works really well on the training set, but you may have overfitted the training set, and you'll find it just doesn't generalize well to the validation set. So that's what you use the validation set for. You have the training set, as I said, might be 60% of your data, and you're trying to find out a good model. You're trying to train, train a model so that it works pretty well for the training set. But, you know, before you accept the model, you test out how well it works on the validation set. And you might use several different models, and you say, well, okay, the model that seems to generalize well from the training set to the validation set is the one we'll use. Okay. And then you hold back the final 20% of your data, which we'll call the test set, because you want some data that's uncontaminated with the whole process that you've used to choose the model to reach conclusions about how well the model works. Okay, so when you sort of produce statistics on, you know, I'm predicting house prices, the standard error of the house price is such and such, you would use the test set. Okay, So you use the validation set to choose your model, but you use your test set to produce, to work out as a final test for how well the model works. Okay, a final out of sample test. So, here's an example. This is a little baby example that I use in the book, but, this is actually, it's about predicting the salaries of people in a certain profession. And you collect some data and you find that this is actually a fifth order polynomial on the left-hand side, and that fits your training set really well. But it doesn't generalize well to the validation set. And so you would say that if you went with that model for the training set, you would be overfitting. You'd be capturing, all sorts of idiosyncrasies of your training set that won't generalize well. Now, if you just went with a straight line model, you would be underfitting, because there is some, the salaries as a function of age sort of trail, it's not linear throughout a person's life. It trails off as the person gets older. So we'd refer to this, model as underfitting, and the best model might well be a sort of quadratic model. In fact, in the example that I use in the book, the quadratic model is the one that generalizes best. But you get the idea, okay? So you might come up with this model on the left-hand side for your training set, and you think, geez, this is a great model, very, it fits the data polynomial, but we'll come across other measures of model complexity. And as you increase model complexity, of course, your model gets better. If you add extra terms to your model or make the model more complex, it's going to fit the training set better. And that's what the solid line is indicating. But as you increase model complexity, you also want to see how well your model generalizes to the validation set. And, you may find, well, the model works pretty well for the validation set sort of here. And then at a certain point, the model starts to not work so well for the validation set. It doesn't generalize well, and you get this gap between how well the model works for the training set and how well it works for the validation set. We're plotting some estimate of model error on the vertical axis here. And, so what you will be looking for is your best model is this, point here, which I represented by X, which is, you want to make your model as complex as you can while it still generalizes well from the training set to the validation set. I mention all this because sometimes machine learning gets a bad reputation because people don't do this. They say, well, geez, let's go for the best model possible as far as the training set is concerned and not worry about whether it generalizes or not. It's important to make sure that you handle that well. Okay, that brings me to the end of the introductory section. Maybe if there are any questions or comments anybody has, we could take them now.
Actually, we have one question.
Okay.
Ariel asked us, is there a name for that sweet spot between the bias and variance?
There may be a name for the sweet spot. Yeah, it's the best model. I don't know that I have a name for it. But I think what you'll find machine learning people talking about is this bias variance trade-off. I mean, that's really what the best model, it finds the best trade-off. I mean, when you're in this region here, you're underfitting, right? Because your model's too simple, basically. And when you're in this region here, you're overfitting. And okay, but I don't know of just the best model.
Okay, thank you. That's the only question we have, so we can move to the next section.
No other questions? Okay. So let's now move on to talking about neural networks. This is neural networks. If you think about my book, I think neural networks is chapter 6 in the book. So there's quite a lot I cover before we get into neural networks in the book. But I thought, for this group, it was more, neural networks was one of the most interesting topics to talk about. So, and there's no question that neural networks, are probably the single most important tool that machine learning people use. Okay, so here's a neural network, or artificial neural network, if you like. Okay, so let me sort of talk you through this. What we have in a neural network, artificial neural network, is what might be termed an input layer, or what we call an input layer, which is really all the features. So let's suppose we're using a neural network to predict something, say the prices of houses in Montreal or something like that, right? So the input layer would be all the features of the houses that we have information on, okay? So those are our inputs. And the output, well, there might only be one output. The outputs are over at this end, and that would be the price of the house, okay? But there's no reason. You can have multiple outputs if you want to, but more often than not, you're just going to have one output, which is the thing you're trying to predict. Okay, so what are we doing in this neural network? The normal sort of models that we're used to, things like linear regression and so on, directly try and relate the outputs to the inputs. Okay, so we sort of write down an equation that says we're hypothesizing that the relationship between the outputs and the inputs is whatever. Okay, and then we estimate the parameters of the equation. That's the sort of standard way of approaching. So neural networks are different in that we say we don't really know what the functional form of the relationship is between the outputs and the inputs. So we just want to allow it to be pretty much anything we like or anything we want. It's got to be a continuous function, actually, for this to work. You can't be discontinuous function. But apart from that, we can have any continuous function you like. And what we do is we have these things called hidden layers. And what we do is we have a relationship between these V1, 1, V1, 2, and so on are the values at these things, we call them neurons in the first hidden layer. So we relate, the value at this neuron is related to what all these lines show, to all the inputs. Okay, and then this value is also related to all the inputs and so on. So we have a lot of neurons in the first hidden layer, which are calculated from the inputs. And I'll talk about how they're calculated from the inputs in a moment. And then we've got the neurons in the second hidden layer that are calculated from the values of the neurons in the first hidden layer. And so on. So what we're doing, in order to sort of be very general in terms of the function that we're trying to estimate, or the relationship we're trying to estimate, we're breaking the relationship down into a lot of, you could call it sub-relationships, okay? And so we're saying, our output is related to the values in the final hidden layer, and so we go back. And when we do that, the actual relationship that we end up with can be, almost anything, right? We're not making any assumptions about the nature of the relationship. We're just letting the data tell us the relationship. So that's the essence of what a neural network is. One key aspect of a neural network is the activation function. So what you do is, let's consider the calculation of this guy, which is the value of this first neuron in the first hidden layer. What you do is you take a linear sum you could call it, of these inputs. It's actually, you have a constant plus, another constant times the value of this input plus another constant times the value of this input, and so on. Okay, it's just like what you have in linear regression. You have a constant term, and then you have coefficients for each of the values in this input layer. Okay, so that's the first stage. You just form what I'll call a linear sum, linear aggregation of all of these guys. And once you've done that, you then apply an activation function to that linear sum. A popular activation function is the sigmoid function, which is this. Okay, and so y here is just this linear sum that I've talked about, okay? And so, first of all, you form the linear sum, and then you apply some activation function to it, and that's what gives you the value here. And then you have a similar sort of way of calculating the value of the next neuron, and so on. And similarly, to calculate the values at the second hidden layer from the first hidden layer, we use activation functions in the same way. So, I've listed, there's lots of different activation functions that people who use neural networks use. I've listed 3 here. So one point I would make is, if we used a linear activation function throughout this network, what would we get? Well, the answer is we just get a linear relationship, right? Because we'd be combining together a lot of linear relationships. And the net result of it all would be that the output was linearly related to the inputs.
Actually, we have an interesting question.
Okay.
Maxime asked us, could a neuron from, let's say, layer 3 can be connected to a neuron from layer 1, for example, as well as those to layer 2?
Yep, you can do all sorts of things. What I'm explaining here is what might be termed a plain vanilla neural network. Okay, and I think I've got a slide later which shows some of, which explains some of the extensions of all of this. I'm not sure that you'd necessarily want to do exactly what Maxime is suggesting. I'm not sure it would add a lot to connect a neuron in the third layer to a neuron in the first layer. But I mean, let's suppose, for example, that your data, you're not estimating the prices of houses, but you're estimating some relationship that could be time dependent, okay, which often you're doing in finance. Okay, so you're collecting data and you don't want to throw away the timestamp of the data. So we got some data from today, and then your next data from yesterday, and so on. So you've got maybe 10,000 data items. But there's a natural ordering to the data items. Then what you would probably want to do is to relate the values at neurons today to the values at neurons yesterday, because you assume that actually you're estimating a model, but maybe this model slowly changes over time. Okay, so you want to build in some time dependence. So that's one example. But there's the architecture of the neural network is a big thing that's talked about. I'm talking about a relatively simple architecture here. It's a good question.
I have actually another question.
Okay.
Nitin asked us, if we have large data set, then how we divide that data set into 3 parts?
Well, it depends. I mean, normally randomly, right? So you take 60% for the training set, 20% for the validation set, and 20% for the test set. So very often you would, I mean, if you're predicting house prices in Montreal, you would just take all the data you have and just divide it up randomly in the way that I've described. However, if there's a time factor, if there's, if you're saying that, maybe you're estimating a model which is changing slowly through time, you would probably use as your test set the most recent data. Okay, the 20% most recent data, because after all, you're not really interested in predicting things from, 5 years ago. You want to predict things today. So, you play those sorts of games.
So no matter what's the size, like the 60% 2020 is always.
Well, I mean, that's just an indication. I'm not saying you've got to do it 60, 20, 20, but that's typically the division. And as I say, sometimes you'll do it randomly, but sometimes, as I say, if some data is more relevant to the current situation, you'll make sure that's in the test set, because that's the critical measure of how well your model's working.
Okay, thank you.
Okay, so, here's a bit more terminology for you. The constant term in a model in machine learning is referred to as the bias. This bias actually tends to be an overworked term, but so what I said was we formed a linear sum in going from one layer to the next. So when I say a linear sum, there's a constant term plus, coefficients times values. So the constant term is referred to as the bias, and the coefficients in the linear sum, are referred to as weights. Okay, and this, this permeates the whole of machine learning. This term bias and weights. Whenever you're forming a linear sum of something, that's. So what a machine learning person would say is, well, what are the weights in this? How, you have starting values for the weights and biases, and then you update them to make them better and better. Okay, so the same activation functions typically used throughout the network, but let's suppose we were in that situation where we wanted to classify loans. What our output from the neural network would be the probability that the loan will default, or the probability that the loan will be good. Okay, we want, what's the probability that this, loan, we've got all these features here, and what we want as an output is the probability the loan will be good. And we use a maximum likelihood method to determine the objective function, which I won't go into, but the critical thing is, as the output from the neural network, we want a probability between 0 and 1. So the final, final activation function should be something like the sigmoid function, because that gives us a value between 0 and 1. Okay, so almost certainly if we were doing a classification problem where the output's going to be the probability that you're in this class or the probability that you're in this class, then we'll use the sigmoid function as the activation function, which ensures that we get a value between 0 and 1. If if we're predicting a house price, we probably would use a linear activation function for the final, only for the final calculation, because we want, we don't want to restrict the house price too much. Okay, now one thing that you should be worried about a little bit right now is, the way I've been talking, you've got a huge number of parameters in this neural network. You've got all the weights, all of the bias and the weights that determine this guy and this guy and this guy, So, yep, you do have a huge number of parameters. And in fact, here's a little calculation for the number of parameters in your neural network. There are F features. Maybe, you've got half a dozen features that you're inputting. Well, actually 20 in my example here, F is 20. You've got a certain number of hidden layers. You might have 6 hidden layers. How many neurons do you have in each hidden layer? 200 in my example here. And how many things are we trying to predict? Well, let's suppose we're only trying to predict one thing. You know, then the number of parameters is over 200,000. And say, well, you know, that's ridiculous, predicting, you know, 200,000 parameters. So that's something that's very important to keep in mind when you're using neural networks. Obviously, you're not going to perfectly predict 200,000 parameters. So, you know, we'll see how that works out. As far as there is a universal approximation theorem that people talk about a lot, which basically says if you've just got one hidden layer, so forget about all these other ones, if you just have this one hidden layer, then any continuous function can be represented by an artificial neural network with just one hidden layer. One of the problems, though, is that to arbitrary accuracy. Any continuous function can be represented to arbitrary accuracy with just one hidden layer, but you may need a huge number of neurons to do that. And so you know, that's why it's very often better to use, you know, maybe half a dozen different hidden layers, because overall you'll have less neurons for the same accuracy. Okay.
Actually, sorry, we have a question from Etienne again. So the question is, does weight automatically assigned by activation function?
Does the weight automatically define the activation function?
No, is it assigned automatically by the activation function?
Well, okay, the way it works is you decide the activation function you're going to use for any given application. I mean, you might try several activation functions, but so the activation function, as it were, is an input from the user. The weights are determined by the algorithm, and that's what we're talking about right now. Okay, so basically we use this algorithm, which is gradient descent, which you may well have used. I mean, you know, I mean, if you use solver in Excel, for example, which I'm sure many of you have, you know, that solver is using a sort of gradient descent or gradient ascent algorithm. I mean, so basically you've got a lot of parameters that you're trying to determine. Just to make it easy to talk about, let's suppose there are only two parameters, okay? Then you can imagine, you know, you've got an objective function, which is a measure of the accuracy of your prediction, or if we're classifying variables, it's the maximum likelihood estimator associated with the classification. So you've got an objective function, which you want to minimize. Typically, you cast the objective function so that it's something you're trying to minimize. And so you can imagine you've got these two parameters, you know, on, you know, two of the axes, and then you've got a vertical axis, which is the thing you're trying to minimize. Okay, so it's a so what I want you to do is to imagine a three-dimensional graph. Okay, the thing you're trying to minimize is on the vertical axis, and the two parameters you're trying to determine are, you know, the two horizontal axes. Then you can imagine a valley, right? And what you're trying to do is to find the bottom of the valley. And so you say, you start somewhere, you have some starting values for these two parameters, and then you say, well, what's the best way down the valley? And so you say, what's the line of steepest descent down the valley? You take and then you change the parameter values, taking a step down the valley, and then you do the same thing again. Let's now work out the new gradient, or the new line of steepest descent. Take another step, and so on. So that's how this gradient descent algorithm works. You use calculus, you calculate partial derivatives, and work out what the best direction of steepest descent down the valley is. Take a step, find a new direction of steepest descent, and take another step, and so on. And you know, this is you know, obviously when you've got it's pretty easy to do this when you've only got 2 parameters. When you've got 200,000 parameters, it's a lot more difficult.
Yeah.
And this is actually where a key result. I'm very proud that Jeff Hinton, who's a faculty member at University of Toronto, was one of the people who came up with this key idea. It's a very simple idea, actually, for calculating the partial derivatives of with respect to the weights. And it's basically just using the chain rule to calculate partial derivatives, but chain rule in a fairly sophisticated way. So another bit of terminology here, the size of the step you take down the valley is the learning rate. Okay, why don't they call it the step size? Well, they don't, they call it the learning rate. So that's basically what you do, except you're not just doing it in 3 dimensions, you're doing it in many, many dimensions, because you've got many, so you've got to think that actually what you're dealing with is a valley in, 200,000 dimensions, perhaps. Okay.
Okay, thank you.
So, I mean, here's a little, here's a little example. I mean, let's suppose that you are using the gradient descent algorithm to minimize this function here. So this is just a 1-dimensional function, so we can actually draw a nice picture of it. And, you might actually, as you can very quickly determine from calculus, the minimum is at 4, when x equals 4, okay? And actually the minimum value is also 4. So, but you don't know that. So you start with a value of x equal to 1 here. You calculate the gradient and you take a step, right? And that brings you to there. And then you say, well, where am I now? I'm now here. I calculate the gradient again, take another step, and so on, okay? And that's how the algorithm works. And eventually you're going to get, one of the key things in the gradient descent algorithm is the learning rate, how big the step is. Now, if the learning rate's 0.2 in my little baby example here, it works pretty well. You can see that, you start with x equals 1, you calculate what the gradient is, it's -6, and then your rule for calculating the step size is gives you 1.2 as your first step size. So x increases to 2.2. You calculate the gradient. The step size is then 0.720 and so on. So the step size is just the gradient times the learning rate. And you can see that, I told you the best value of x is 4, and you get very close to it after 13 steps, 13 iterations. So that seems to work pretty well with a learning rate of 0.2. So say that what you do is you calculate the gradient at each stage, and then you multiply the gradient by the learning rate. Now, when you're in many dimensions, you've got many gradients, all the different partial derivatives that you're calculating, and but you apply the gradient rate to each one to find the change that that you're making. But this business of determining the learning rate is a big thing in the gradient descent algorithm. I mean, if you make the learning rate too small, your step size will be too small. And yeah, you will eventually get to the right answer, but it'll take you a long time. Okay. And if you make the learning rate too big, then you'll be kind of overshooting always. And as you can see from what happens here, you never get there. So if the learning rate's too small, it just takes you a huge amount of time to reach the bottom of the valley. And if the learning rate is too big, you'll never get there, because you can see from the diagram here, if you're taking really big steps, then you're going to overshoot the minimum, and then overshoot it again and again and so on. Okay, so there's a lot more I could say about, and there's a lot more in the book actually about the gradient descent algorithm. I mean, there's a lot of work being done on calculating optimal learning rates, optimal step sizes. What you want to do, of course, is to avoid local minima. Now this is a nice, well-behaved function, but most of the functions that you actually come across in machine learning have, are nothing like as, they're not convex like this. There's local minima, and you want to make sure you don't wind up in any local minima. So every so often you just take a big step size to get out of a local minimum. So there's all sorts of little tricks, shall we say, in terms of the use of the gradient descent algorithm.
So there is no predefined algorithm or a method to define or calculate the learning rate. It's like more experimentally?
No, there are methods for calculating the learning rate. A lot of things, though, in machine learning are trial and error, and we have give you another bit of terminology. There's this terminology hyperparameter, which is determining a parameter which helps you define the model, but it's not actually a parameter of the model. And the learning rate is kind of like that. It's a hyperparameter. But as it happens, there are, and most hyperparameters, you just have to determine them by trial and error. I get a lot of questions from students, when
I just got a question about that too.
Yeah, every time, I talk about a particular algorithm and it's got hyperparameters, how do you determine the hyperparameter? And the answer is usually trial and error. As it happens, though, to determine the learning rate, there are some clever ways of doing it, and I would point you in the direction of something called ADAM, ADAM, which is short for, I have to look it up actually. It's short for adaptive moment estimation. Okay, and it's basically a way of determining the learning rate. It's and you don't necessarily want to use the same learning rate throughout the whole algorithm. So it adapts. So there are, you don't have to do it entirely with trial and error. Now we go back to what I was talking about in the first module. Here's another bit of terminology, an epoch. An epoch is just going through all your training set data once. Okay, now one of the tricks that you use to speed up this gradient descent algorithm is actually you don't use the whole training set on each iteration. Okay, you maybe use 20% of your training set on the first iteration, and then the next 20% on the next iteration, and so on. It turns out that that's that speeds up things a lot. So you use chunks of your training set in sequence, going right through using the whole training set once. So that might, if you're using 20% of your training set each time, then that will take 5 iterations. That's referred to as an epoch. Okay. So what I'm plotting here, and this is from a particular application, I can't even remember what it was now, but this is a particular application that did, and you've got the epochs here along the horizontal axis, okay, that you're using, and on the vertical axis, you've got the thing you're trying to minimize. And the blue is the training set. Now, it's pretty noisy what happens, but you can see, generally speaking, and what you do incidentally, usually is to calculate a moving average of how well you're doing rather than to look at it for each epoch. But I just thought I'd give you an idea of what the raw data looks like. So what the blue line shows is that things generally get better for the training set, as we would expect. as now increasing the number of epochs is a measure of model complexity, okay? Because we're just sort of delving further and further into this valley and sort of being more and more sophisticated in the way that we're determining the weights, okay? So that, if you like, that's the measure of model complexity that we were talking about earlier, as far as, this is concerned. And what you can see happening to the validation set is that, yeah, it seems to be hugging the training set fairly well, but then it diverges. So you could say, let's stop after 300 epochs, because that's our sweet spot, if you like. That's the, the bias variance trade-off point. So,
Actually,
go on.
Actually, we have two questions. One of them is related to this graph. So Connor asked if, I will just read the question for you. So related to the graph of the complexity and fit, one that you have here in 26, he asked if the complexity is predefined based on the number of hidden layers. And it seems like to add complexity would need to be able to add hidden layers or amount of variables within those layers.
Okay. Good question. There's one of the things, let me go back a few slides and have a look at this picture again. I mentioned hyperparameters a moment ago, and the hyperparameters that we have are the number of hidden layers and the number of neurons per layer. Okay, so those are two hyperparameters. What we do and there's no good way of choosing, I mentioned how you could choose the step size, the learning rate using Adam, but there's no really good way of saying, do I need 6 hidden layers? Do I need 10 hidden layers? Should I have 100 neurons per layer, and so on? So that is something you do with trial and error. Typically what you do is you just make the model more I should say, make the network more and more complex. But each time you sort of increase the complexity of the network, it's a new model, or a new run of your algorithm, okay? And you go on increasing the complexity until your model doesn't improve. Okay, that's typically the way things go. So you will go on increasing the number of hidden layers and the number of neurons per layer. Each time you run the model, you will be doing what's sort of described here. Okay?
Okay.
So it's, so they're two separate things. Okay, because you'll have a different stopping rule each time you run your model. And on this particular run of this particular model, the stopping rule was to stop after 300 epochs. So typically, obviously you don't have to write your own software for doing this. There's no end of packages in Python and other languages for doing this. I mean, typically what you do is you say, well, let's, when we get to say 400 or 500 epochs, we sort of say, well, have things improved over the last 100 epochs? If they haven't, then we should have stopped 100 epochs ago. Those are the sort of rules that we use. Okay, there was another question.
Yes, the second question is from Michel. He said, I've seen it mentioned before that local minima aren't a problem in certain cases because of the presence of the saddle points, where at least one dimension has a non-zero gradient. Is this the case the more dimensions or features we're looking at, or is there a different cause?
Yeah, I mean, I mentioned this earlier. I mean, local minima are a problem, and, saddle points can be a problem as well. And that's where some of the finer points of neural networks come in. I don't have slides to discuss these finer points, but the sort of thing you want to do to, Actually, this business of using mini batches of, maybe dividing your data up into a number of batches and so on means that actually helps as far as what we're talking about here, because what it means is that, if you're going down a valley, you're going down the valley in a more zigzag way rather than straight down, because you're not using all your data on each iteration, and that actually helps because you're exploring more. So it's not so, although you want to go down the valley as efficiently as possible, you want to do a little bit of exploration along the way. And so the algorithms that are actually used in practice do that. And also, as I say, every so often you might want to take a big jump. Big learning rate is a big learning, just to, if you reach one of those saddle points, just to jump out of it and see whether you improve. So there's all sorts of little tricks like that.
Okay.
Yeah, because.
And actually.
Yeah. Okay.
Oh, sorry. For Connor, well, he's thanking you for your great answer about the previous one, and he's asking if there is a way to add layers recursively.
Add layers recursively. I don't know quite what he has in mind there, but I think every time, I think it's basically, maybe he's thinking that, I've run the model with 6 layers. How would it work with 8 layers? As far as I know, there isn't any quick shorthand for doing that. You've just got to rerun the model with 8 layers. You can't say, well, is there a quick way of adding 2 layers to an existing model? As far as I know, there isn't. Okay.
Okay.
So this is, this business of when to stop is a key thing, and it sort of takes a bit of if you're used to sort of optimization problems where you go right to the optimum, that's not what you do in neural networks. You don't find the actual bottom of the valley, because the bottom of the valley, even if you could find it with 200,000 parameters, would be an incredibly complex model, and it wouldn't generalize well. So what you're doing, and I emphasize this, is you're running your model with the training set, seeing how well, sorry, that's the blue one, seeing how well you're doing, but at the same time, you're running the model with the validation set. Okay, because you want to find that sweet spot. How, and it just turns out, your model is becoming more and more complex as you do more and more epochs. Okay, so this, this slide, there's huge amount one can talk about as far as neural networks are concerned. They are, very important tool within machine learning. What I've listed here are just some of the extensions of this basic neural network model that I've talked about. So maybe I'll just, run down these a little bit. But I mean, autoencoders are a neural network where the output is the same as the input, which is very strange. And of course, if you, I mean, let's suppose, going back here, if we had, just say 3, well, no, 3 isn't a very good example. Suppose we have 8 inputs and we have 8 outputs, and we have at least, we have, at least 8 neurons in the hidden layers, then, predicting the outputs from the inputs would be straightforward. But what we do in the middle of our neural network with an autoencoder is just have a small number of neurons compared with the number of neurons we start with. In other words, we use the neural network to try and extract a small number of manufactured features that give us more or less the same information as the input layer. I mean, an example I use with students for autoencoders is interest rate changes. You know, let's suppose you've got eight different points on the term structure of interest rates: the 1-year interest rate, the 2-year interest rate, the 3-year interest rate, and so on. You could regard those 8 interest rates as being sort of separate variables that you've got to keep track of, but we all know that actually when the 1-year interest rate goes up, the 2-year interest rate tends to go up as well, and so on. So what we're trying to do is to find manufactured features that represent what's going on with the interest rates. And we can do that. So we start with 8 inputs. And then the actual architecture of the neural network doesn't look like this, because those 8 inputs are reduced to 2 neurons in the middle. And then the 2 neurons go back to the 8 outputs. And we see if we reduce the 8 inputs to 2, shall we say, I'm just using 2 as an example, to 2 latent variables, which are, you know, 2 neurons in the middle of the network, that we can represent the data. So that, you know, that's, I obviously don't have time to go into all of these extensions of the basic neural network in detail, but, you know, that's what autoencoders are for. Variational autoencoders are for generating sometimes you don't have enough historical data to do whatever analysis it is you want to do, but you can generate data that is indistinguishable from the historical data. And variational autoencoders are one way of doing that. Generative adversarial networks are another way of doing it. You know, convolutional neural networks, you know, are yet another, you know, way of designing the architecture of neural networks. Recurrent neural networks are what I briefly talked about before, which is where you might want to relate the network, the values of the neurons today to the values of the neurons you had yesterday, so that your model kind of evolves through time. And long short-term memory networks are an extension of that idea. So, you know, obviously this is an introductory presentation, so I'm not going to you know, spend, you know, too much time on all of these, but I just think it's important to emphasize that, you know, the first thing you want to do is obviously master how the basic neural network works. But once you've done that, then you'll see all sorts of clever ideas for changing the architecture of the neural network to actually sort of achieve, you know, particular results that you're interested in. Okay, I think that's the last slide I have on neural networks. So are there any, you know, any additional questions before we move on?
So far there is no, but I don't know if there is anyone who wants to ask any question. Yeah, we have one question. What is currently the best way to apply neural networks to derivative valuation and risk management, and what kind of neural network architectures are used in this field?
Well, that's a big question. I have a, maybe I'll just answer it. I mean, actually, it's a good question. And, you know, it does illustrate one important application of neural networks in the derivatives business. Some derivatives that are out there, you know, are plain vanilla derivatives, and we've got a nice simple formula like Black-Scholes for valuing them. Other derivatives are referred to as exotic derivatives, and, you know, very often they've got to be valued with Monte Carlo simulation or some other procedure. And, you know, that's fairly time consuming. So if you've got the trader on the phone to a client and the client says, well, what would it cost me to buy this exotic derivative? And, you know, the trader has got to sort of run some software that takes 3 minutes. That's not good. So interestingly, what a lot of banks are doing now, a lot of derivative dealers are doing now, is to come up with neural networks that let's go back to our picture here. Neural networks that kind of imitate how Monte Carlo simulation values this particular exotic derivative. So you've got the inputs to the derivative. These are all the features of the derivative and the environment and so on. And you've got an output. You might have more than one output. You might want to know what the Greek letters are and that sort of thing. But the key thing is, once you've developed this neural network, valuing the derivative is really fast because you're just working forward through the network. You know what the weights are, you know what the activation functions are. So once you've got the neural network, calculating these, the values at the first hidden layer, the second hidden layer, the third hidden layer, and so on, very fast because you're just working forward through the network from known inputs to outputs. So, a neural network will improve the valuation of these exotic derivatives by, huge numbers of orders, 4 or 5 orders of magnitude, typically. How do you develop the neural networks? Well, you've got to do a lot of upfront work to develop the neural network, because what you've got to do is to create a lot of data using your Monte Carlo simulation value tool to relate outputs to inputs. So you do a lot of work up front, create a training set and a validation set and a test set, running your Monte Carlo simulation over and over and over again. Okay, and then you say, okay, I've got lots and lots of data. Now let's ask the neural network to, to create, or ask the algorithm to create a neural network that relates the inputs to the outputs. So yeah, that's that's a very popular application. And I've got some examples in the book on it. Okay.
I have other questions actually. Nitin is asking how to decide the number of hidden layers precisely.
Well, as I say, you get number of hidden layers and number of neurons per layer. You just go on increasing it until accuracy trails off. Okay, so basically that is a trial and error. There's a trial and error hyperparameters. Okay, you obviously don't have a very simple neural network because that's not going to capture the essence of whatever nonlinear function it is you're trying to estimate. But neural networks, the architecture can be more complicated than it needs to be, and so it's a trial and error process.
Okay. And Matisse is asking, do we necessarily have overlearning when the network becomes more and more complex?
No, the overlearning or the overfitting is, is a question of, whatever neural network you use, it's the number of epochs that you've done. Okay, so, you could have overfitting with just 6 layers, you could have overfitting with 20 layers. It's, as I say, you're going to be stopping. You're going to have a stopping rule, however many layers and number of neurons per layer that you have.
Okay, and
okay, yeah. Maybe just one more question because we want to.
Yeah, it's the last question actually. Yeah. Yisan is asking, do you think generative models could replace Monte Carlo simulations?
Well, I'm not sure you're using the word. I mean, what replaces the Monte Carlo simulations is a neural network. Okay, as I say, and it is. It is replacing Monte Carlos. Generative networks are used to create data that is similar to the data you started with. We don't need generative networks because we can run our Monte Carlo simulation as many times as we want to. We're not short of data. When we're creating the data, that's a nice situation to be in. We don't need to use generative networks. So it's just a regular network designed, as I said earlier, to, replace, or I should say, to replicate results we get from Monte Carlo simulation. Okay, let's move on to the third module that I want to talk about, reinforcement learning. And as I mentioned earlier, reinforcement learning, another important tool in machine learning, which, as I say, I tried to sort of introduce you to what I consider to be the two most important tools that are, as it were, almost unique to machine learning. So it's concerned with finding a strategy for taking a series of decisions rather than just one. And usually, as you're taking these decisions, the environment is changing, which is, a complication. So here's a picture of, this is my picture anyway, of how reinforcement learning works. Other people use different pictures, but, what we work with in reinforcement learning is states and actions. Okay, the state is defining the environment and the action is the decision we take. Okay, so that's the terminology. We've got states and actions. So the way it works is we've got an initial state and we take a certain action. That leads to some result, and we call the result might be a cost or it might be a benefit, but we call it a reward, okay, in machine learning. Okay, so there's a reward and then the state changes. Okay, and then we take another action and we get another reward, which might be positive or negative, and the state changes again, then we take another action and so on. The example of this that I've been working on in my research quite a lot is hedging of derivatives. Because if you know anything about derivatives, hedging is a multi-stage decision problem. You got this derivatives portfolio, you take some action to hedge the derivatives portfolio, then the world changes. You rebalance your hedge, the world changes again, you rebalance your hedge, and so on. So, I mean, that's, this is one example of reinforcement learning, but there are many others. Actually, I think my examples are in a later slide, but you've probably all heard about computer programs that can beat any human being now at games such as chess and Go. And, I was a really keen chess player in my youth, so I've been very interested in, in all these, algorithms to play chess. And, the early algorithms to play chess basically used chess grandmasters to program the algorithms and evaluate positions and that sort of thing. But the more successful recent algorithms, the name of the algorithm AlphaZero, produced by Google researchers. Basically, all you do is you just give the algorithm the rules of chess. You program the rules of chess or any other board game you happen to be interested in. And what the algorithm does is play against itself many, many times and learns. So you don't actually have to say, if you get to this position in chess, then it's a winning position. The algorithm learns all that. And so, probably of the more traditional algorithms to play chess, the best one is probably Stockfish, which you may have come across, and that does build in, human experience. It sort of involves chess grandmasters in programming the algorithm, but Stockfish can be beaten by AlphaZero. Is beaten by AlphaZero, and AlphaZero is just an application of reinforcement learning. Basically, because playing chess or Go or any other board game is a multi-stage, decision problem. Yeah, you're going to do a move, Then your opponent's going to do a move, and that changes the environment. Then you've got to make another move, and your opponent will change the environment again. So, you know, it's a classic application of reinforcement learning. It's and a very successful one. I mean, it's pretty incredible that you don't have to tell the software anything except the rules of the game. And it would just, at the end of a few days of learning, it's much better than the best human chess player, and the same applies to Go and other board games. What else? I mean, there's been applications of reinforcement learning in medicine, because treating a patient is a multi-stage decision problem. You know, you try something and you observe the results, try something else, and so on. Okay, so what, you know, let's sort of get into this a little bit. One of the key things in reinforcement learning is this exploration versus exploitation trade-off, if you like. Because how do you come up with the best strategy to play chess, or to, you know, to hedge a derivatives book or whatever? Basically, it's a trial and error kind of process. You start with a certain strategy, and then you refine it, and you refine it, and you refine it. And so one of the key things that you've got to do in reinforcement learning is to decide on each iteration of your strategy, am I going to explore or am I going to exploit? In other words, you know, I've got a certain amount of experience because you know, if I'm playing chess, I've played chess against myself 100 times, and I've got a certain idea of, you know, what the best decision to make in this position is. Should I exploit? Should I just take the best decision that I've seen so far? But then I'm never gonna, you know, if I do that, I'm never gonna get any better. You know, so every so often I just want to explore something new. So that's the key thing in these reinforcement learning algorithms. How, you know, when you start off developing an algorithm to do something like play chess or hedge a derivatives book, the algorithm doesn't know anything. And so it's going to be 100% exploring. But then as time goes by, it learns. And so it doesn't want to be 100% exploring. And so the idea is you start 100% exploring, then you reduce the amount of exploration, and in the end, you're 100% exploiting, and then you've stopped. Okay, so that's the critical thing. How you, you know, how you find this trade-off between exploring and exploiting. So, you know, typically at any given stage in an algorithm, there's a probability, we'll call it epsilon, that you will explore, which is just randomly choosing some decision. And there's a probability 1 minus epsilon that you will exploit. And as I say, when you start off, epsilon is 1, because you don't know anything, so you've got to explore. And then as time goes by, you reduce epsilon. And the decay factor is the way in which you reduce epsilon through time. So, for example, you know, if the decay factor was 0.995, then the probability of, you know, exploration would on one trial would be 99.5% of what it was on the previous trial. So your first trial, 100% chance of exploring. Second trial, 99.5% chance of exploring. Next trial, you know, 99.5% squared chance of, you know, exploring, and so on. How do you determine the decay factor? It's a hyperparameter, and it's going to be typically determined by trial and error. Okay, So first, simple example to illustrate reinforce. I actually, in the book, I used two examples. And the first one is what is a well-known example, actually, in machine learning and in statistics. It's the K-armed bandit example. So what this example is, you're in a casino, there are K levers. Let's say K's 4. So there are 4 levers which provide normally distributed payoffs with a standard deviation of 1. You know the standard deviation is 1, but you don't know what the mean is. Okay. What strategy should you use to maximize your total payoff over many trials? So this is the classic decision. You'll first time you'll pull a lever, you can choose a lever at random. The first time you observe the result, that doesn't tell you too much. You're probably going to continue to explore for a while, and then eventually you'll build up some information about these normal distributions which you're getting from each lever, and then you'll start to exploit. So here's one of the outputs that I use. So let's suppose the expected payoffs from the levers are 1.2. So these are the means. Remember, the standard deviation is 1. The means 1.2, 1, 0.8, and 1.4. So if you knew those means, you'd just pull lever 4 every time because that's got the best expected payoff, but you don't know that. So you start at epsilon, you start at 1, and I'm actually using a decay factor of 0.995 here. So here's one possible trial. You choose, and you'll find on my website all sorts of software to go with the various things I've talked about today, which tie in with the book. So on the first trial, you might choose, just by chance, lever 2, and just by chance you get a pretty good payoff of 1.4. So the Q value is your best estimate of the payoff from whatever lever it is you've chosen. So you might start with a Q value of 0 for all the levers. That's typically what you do, and now you can change the Q value to 1.4 for lever 2. Then you explore again on the next trial because it's still a very high probability of exploring, and you choose lever 1, which doesn't give you a great payoff, and so on. And so it continues. And on this particular trial, you're exploring for all the trials that we're looking at here out to trial 100, and then you start to exploit because you're learning quite a bit. And so you can see that on trial 100, let's see, what have you done? On this particular case, you've chosen lever 4 30 times. So you're beginning to learn that lever 4 is, you've probably done some exploiting. You've chosen lever 2 20 times. You've chosen lever 3 20 times, lever 2 31 times, and lever 1 19 times. So, some randomness there, maybe a little bit of exploiting. By 500 trials, you've used lever 4 361 times. So you're starting to learn that this is the best lever. By 1,000 is 850 times. So, and, 5,000 trials, you've nearly, 4,849 out of 5,000 times you've used the lever. And the critical sort of thing as to whether this has been a good strategy is what your average gain per trial is. Now, you haven't managed an average gain of 1.4, but it's pretty close. You've managed 1.38. So, this is a very simple example of reinforcement learning. And one of the reasons why it's simple is the environment is not changing. Okay? The mean payoffs from these levers are staying the same throughout all your trials. So all you're doing is just trying different things and monitoring the results. Okay. Now, my second example, which is, I think, in many ways a more interesting example, is NIM. This is my own example. I don't know whether you've I don't know whether you've heard of this game NIM. Most people haven't, but it's a simple game where you've got to imagine there's a pile of matches. It's a two-person game, and there's a pile of matches on the table. And each player picks up 1, 2, or 3 matches. Okay. And what you want to avoid doing is being the last person to pick up a match, because then you lose. Okay. So you could talk, you have 100 matches on the table, and if pick up 1, 2, or 3 matches, the last person to pick up a match loses. Now, it's actually, if you think about it a bit, you can work out what the best strategy is for NIM. This is what makes it an interesting game. We can analytically work out what the best strategy is. And the best strategy is to leave your opponent with 4n plus 1 matches, where n is an integer. Okay. So, if we're getting towards the end of the game, put n equals 1, you want to leave your opponent with 5 matches. What's your opponent going to do? However many matches your opponent picks up, you can, on the next round, leave your opponent with just 1 match. Because, 5 matches left. If your opponent picks up 2 matches, you pick up 2 matches. If your opponent picks up 3 matches, you pick up 1 match, and so on. So as I say, clearly you will win if you can leave your opponent with 5 matches, and then you can extrapolate from that and say, well, if I leave my opponent with 9 matches, which is 4 times 2 plus 1, then on the next round, I can make sure my opponent's only got 5 matches, and so on. So, if you can, if you start off playing this game, that's how you can be sure of winning, assuming that you're playing. Of course, if your opponent goes first, then your opponent might leave you with 4n plus 1 matches, or maybe you're going first, but there's actually 4n plus 1 matches out there. So you're not certain to win, but this is a winning strategy if your opponent doesn't know what they're doing. So I've created this little game. Your opponent behaves randomly. That's an assumption, although I've got extensions of the game which where where you learn a lot faster, because your opponent doesn't behave randomly. Your opponent behaves well. Your opponent is learning at the same time as you're learning, which is actually kind of an interesting extension of what I'm talking about here. But so we can say the reward is +1 from winning and -1 from losing. Actually, it's kind of interesting just to go back to AlphaZero. If you sort of read some of the documentation on AlphaZero, you'll find that what AlphaZero does, as far as reinforcement learning is concerned, is have a reward of +1 from winning the chess game and 0 from losing the chess game. And what that enables AlphaZero to do effortlessly is to say at any given time, what is the probability that you will win? Because, any given strategy is going to say, well, maybe, your Q value is 0.65, which means you've got a 65% chance of getting +1 and winning, and a 35% chance of getting 0 and losing. But actually, we've done something a bit different here. I've done, and this is just arbitrary, +1 from winning and -1 from losing. So here we do have states and actions. The state is the number of matches, and the action is the number picked up. And you can play this game with any number of matches up to 100 from the software that's on my website. But let's just consider a nice, simple situation of something definitive to talk about, where there are 8 matches initially. Okay. So we know, and it's you go first, there are 8 matches. So we know your best strategy is to pick up 3 matches. Leave your opponent with 5 matches and you win. But the algorithm doesn't know that. So the algorithm has to learn that. So what the algorithm starts out with is a table like this, okay? And the table has these 8 states, which is the number of matches on the table, and the 3 actions that you can take, which is pick up 1 match, pick up 2 matches, pick up 3 matches, okay? And basically, you just do trials. So on the first, I'm assuming in what I'm presenting to you is that your opponent behaves randomly, which means your learning experience is not as good as it might be, because your learning experience is a lot better if your opponent behaves sensibly. But you can, as I say, you can explore that with some of the software that I provide. But so let's suppose the first trial, you're just behaving randomly. You pick up 1 match, your opponent picks up 3 matches, you pick up 1 match, and then your opponent's stupid, picks up 3 matches because your opponent's behaving randomly, you win. What can you do as a result of that trial? Well, actually, what you can say is when there are 8 matches on the table and I picked up 1 match, it worked out pretty well. So I'm going to update what I'll call Q81, which is, all the numbers in this table are 0 initially. I'm getting some information about this number. 8 matches on the table and I pick up 1. So I update that. And actually, when there were 4 matches on the table and I picked up 1, it worked out pretty well as well. So I'm going to update Q41. Okay, so as a result of this trial, what I can do is I can update this number here and this number here. And the updating formula that is used in machine learning typically is this. So I update it by say, well, whatever the old value is, kind of like a, it's a sort of fairly popular updating formula in statistics. You have the old Q value and then you take some parameter alpha again. This is a hyperparameter that's going to be determined by trial and error, but 0.05 is typically a good value for this parameter. You multiply that by the gain minus whatever the old Q value was. So you actually gained 1 on this trial because you won. So you say the new Q value is the old Q value plus 0.05 times 1 minus 0, which, where are we? Do I have the, okay, I haven't given you the new, yeah, I've got some examples coming up later, but I haven't. Okay. I don't seem to have the table. But basically, the next table is just going to have this number updated and this number updated to something like 0.05. And then and then we continue like that. And on each trial, we observe certain states and take actions in those states. And what we do is we have this exploitation versus exploration trade-off. So there's a certain probability that we will explore, which means we'll randomly choose our decision. And there's a certain probability that we'll exploit, which means we just take a decision corresponding to the best Q value that we've got so far. So, there's two main methods that I want to mention, but what we've been talking about so far is what's known as the Monte Carlo method, which is basically you wait till the end and see how well the game worked out. So, here we've got some, statistics on, what happens as we use more and more trials here. So after 1,000 trials, and remember, initially we're behaving randomly, but we're applying this decay factor of 0.995. So, we're doing more and more exploitation as time goes by. So after 1,000 trials with Monte Carlo method, what we see is that it hasn't really found the best decision here yet. Actually picking up one match looks a little bit better than picking up 3 matches when there are, 8 matches left. It doesn't do anything for 7 matches because actually, given that you pick up some matches and your opponent pick up some matches, you never actually have to take a decision when there are 7 matches on the table. When there are 6 matches left, yeah, we know the best decision when there are 6 matches left is to pick up 1. And it's kind of found that. Doesn't know what to do with 5 matches and so on. When there are 3 matches left, yeah, it's definitely best to pick up 2 matches, and it's sort of found that out. And when there are 2 matches left, it's definitely best to pick up 1 matches. So, it's found those decisions, those are easy decisions, pretty quickly. Then after 5,000 trials, you can see that it's learned a lot more. With 8 matches on the table, it's learned that it's best to pick up 3 matches. That seems to be pretty clear cut. It also, and this is because your opponent's behaving randomly, it doesn't look so bad to pick up 2 matches or 1 match. But in fact, if your opponent was actually learning as well, these numbers become negative numbers. And so the learning the best decision is a lot crisper if your opponent is, as I say, behaving reasonably sensibly, as opposed to behaving randomly. 6 matches left, yeah, we're beginning to see that picking up 1 match is optimal and so on. And then, otherwise, and then again, we see that after 10,000 trials, we're even closer to the best decision. As I say, what I don't really like is that we've got, 0.910 as the value of picking up 2 matches we wouldn't get that if we had, our opponent behaving sensibly. Okay. So, whoops, did I get, sorry, so this is what we get from the Monte Carlo method. Now, the other method that I want to mention is something called temporal difference learning, or Q learning, which is an important extension of the Monte Carlo method. And what we do in temporal difference learning is we don't look to the end of the game to see whether we won or lost. What we look to is to say, well, look, if we pick up 1 match, okay, and our opponent then picks up 1 match, how valuable is that position to us? We don't need to wait till the end of the game. We can see that if we pick up 1 match and our opponent picks up 1 match, then this is worth 0.831 to us. So we could use that 0.831 to update our Q values. We don't, we don't need to, because this point, to some extent, this 0.831 reflects, sorry. I guess I should be looking at this. I should be looking at this slide because we are talking about temporal difference learning. So, I mean, let's say if you pick up 1 match, your opponent picks up 1 match, the situation looks pretty good. Okay, so you don't need to wait until the end of the game. You can use this 0.997 when you're after 5,000 trials to update the Q value. So basically, temporal difference learning is where you update the Q values by looking just 1 step ahead, as opposed to looking to the end of the game. And if you compare this slide with the previous slide, you'll see that it actually works more efficiently. Than, you know, so, and that's generally true, that temporal difference learning works better than the Monte Carlo method. So just to summarize, the Monte Carlo method, you look to the end of the game. Temporal difference learning, you just look to the next step, which is when you next have to make a decision in the game. And as I say, you know, these numbers get improved a lot, actually. I haven't got slides on it, but get improved a lot when you actually let your opponent learn. You learn the best decisions much more quickly. Okay, we're not doing too badly on time, actually, because we're nearly through this now. When there's many states or actions, you know, I mean, you know, this little baby game is a nice little illustration, but of course, many of these situations we encounter in practice, you've got many different states and many different actions that you can take. So, you know, this table, you know, it's got lots and lots of columns, lots and lots of rows. And the problem then is that the table doesn't get filled in very quickly as you try out different strategies. Okay, you know, it's sort of, you know, I mean, if you have 20 different actions and 50 different states, you know, then you're going to have, what, 1,000 cells in the table. It's not, the table's not going to get filled up very quickly. So what do you do then? And, you know, the answer is that you can then blend in reinforcement learning with neural networks. So you can use a neural network to, as it were, fill in the table, because the table, you know, is just going to be a nonlinear function of, you know, the states and the actions. And you've got some, you know, you've got some observations to help you determine this nonlinear function. And so you just use a neural network to, you know, define the complete nonlinear function from the observations you've got. Okay. So this is known as deep Q learning or deep reinforcement learning, where you're combining reinforcement learning with neural networks. So we've really covered this off. Lots of applications. Say, you know, really interesting to sort of do some Google searches on the computer programs that play Go and chess. So applications of reinforcement learning. I talked about healthcare. I've talked about hedging. Optimally selling a large block of shares is another important application of reinforcement learning, because, you know, and you know, something which, you know, is now part and parcel of what all financial institutions do. If you've got to offload a large block of shares, or indeed if you want to buy a large block of shares, you may not want to put your whole trade through at once. You may want to do it in stages, because if you're selling a lot of shares and you put a big trade in, it's going to move the market. So you want to bleed your trade into the market bit by bit, and that's a reinforcement learning decision. And you know, portfolio management, where there are transaction costs, as there nearly always are, you know, how do you change your portfolio to as you observe the environment changing. Hedge funds, large asset managers, they're all using machine learning to help manage their portfolios these days. It's a big new development in the market. So if you want to, you know, learn more about all of this, I'd encourage you to get a hold of a copy of my book, which, as I say, you can read more about the book on my website, and you can also see a lot of the stuff that goes with the book on my website, because there's a lot of software, you know, some of the applications we've talked about today, you know, things like NIM. For example, there's a lot of software to illustrate that on my website, as well as software for that derivatives example that somebody brought up, which is where you want to create a neural network to replicate what Monte Carlo simulation does. There's, there's an example of that on my website as well. So, any final questions about reinforcement learning?
Thank you very much for your informative and interesting presentation, Dr. Hall. Actually, now we will wrap up with a section of question and answer Q&A. Feel free to write it in the chat or actually unmute yourself and you can ask directly the question. That will make it a more interactive way. So we're waiting for your questions.
I think
I have a
it's
question.
been a long morning. Yep. Okay. There's a question. Okay.
When Google says that it has a new AI that supposedly is able to play any game you give the rules to, how is that? How does that differ, I guess, from typical reward systems?
Well, I mean, I wouldn't put it quite that way. I would say that they've got an application of reinforcement learning. As I say, AlphaZero, which is the best chess playing program out there, the reward system is 1-0. So you get 1 if you win the game and 0 if you don't win the game. And at any given stage, you can look at all the Q values and see what your chance of winning is. So it's just an application of reinforcement learning. It's much more sophisticated than, or I wouldn't say much more sophisticated. It's much more much better than sort of any other method for playing these board games that's been suggested. I mean, you all will perhaps remember when IBM produced this computer that beat Garry Kasparov. I don't know, 20 years or so ago. I mean, I think, the games that computer played with Garry Kasparov, who was the world champion at the time, indicated the computer was about as good. It wasn't a huge amount better. And that was a computer that had been programmed by grandmasters. And what we're saying is that just, you don't need to give the computer any information about how humans play these games. It'll learn. It'll learn and it'll get better than any human being. It's a big triumph, in my opinion anyway, a big triumph for reinforcement learning.
Hello, Professor. I had a question. Can you hear me?
Yes, I can hear you.
Yeah. So which machine learning algorithm can be used for hand gesture recognition?
Sorry, for what?
For hand gesture recognition. For hand gesture recognition.
Oh, hand gesture recognition. Jeez. I don't know. Where it's, I mean, it sounds like a classification problem to me. But where are you going to get your hand gestures from? Have you got a good data set for hand gestures? I mean, basically, you've got to have a labeled data set to start with, and then, But yeah, I mean, this is one aspect of machine learning that we haven't really got into, which is sort of using machine learning for images. I mean, because I'm a finance guy, I mean, I've been mostly interested in using machine learning for numerical data.
Okay.
I do have I do have a little bit in the book on, recognizing images, but that's what you're talking about. You're saying, well, if I use one hand gesture,
Yes, yes, right,
You know, it's
right.
got some data on hand gestures, and it's sort of, you know, but not every hand gesture looks the same. And, you know, that's, you know, that's an image recognition problem. And you know, it's, you know, it turns out that, you know, neural networks and other tools can be used for that. You've got to convert the image into numbers first. So, you know, you got to look at all the pixels of the image, and then the algorithm has got, and actually this is, you know, I mentioned one of the extensions of neural networks was convolutional neural networks. That's actually the sort of thing that convolutional neural networks are designed to do, to recognize images. So, you know, probably my short answer to your question is, yeah, you wanted to look into convolutional neural networks.
Yes, yes, yeah. Thank you, Professor. Thank you.
I mean, you know, one of the classic data sets actually in machine learning is, you know, recognizing numbers, how people write numbers. You know, you might write the number 2 differently from the way I was write the number 2, and you want to train a machine to sort of recognize you know, these numbers regardless. And you know, it's you know, it's one of the standard data sets that people use to, you know, test out different algorithms.
Oh, okay.
Yeah,
Thanks.
so your data set sounds like it might be similar.
Okay, thanks.
Actually, we have 2 questions on the chat section. One question is, does regulators Basel 2 and 3 accept machine learning applications in finance?
Well, it's it's a challenge for regulators, just as it's a challenge for everybody, you know, to you know, and I do talk to the regulators quite a bit about this. You know, they have some expertise, probably not as much expertise in machine learning as some of the companies that they're regulating. So my advice, you know, so the answer is, yeah, regulators obviously will accept machine learning applications, but they're going to apply the sort of test to them that we've talked about. You know, they want to make sure that there's a training set, a validation set, and a test set, and they've been used appropriately. So that's, you know, one of the things regulators are getting used to. And the other general thing about the regulation of financial institutions, or banks in particular, I should say, which you talked about the Basel Committee, is that they require any model the bank uses to be re-evaluated every year, and not re-evaluated by somebody who's different from the person who developed the model. And that applies to machine learning models as well. So yeah, I don't think the regulators have ruled out machine learning models altogether, but they're naturally cautious about, you know, about them. And, you know, they want to see a lot of documentation, and they want to see that the model has been implemented in a good way.
The next question is, can reinforcement learning be used in conjunction with some algorithms which use learning techniques based on biology, such as particle swarm and colony genetic algorithms, etc.?
Oh, yeah, a bit outside my area of expertise there. Yeah, I mean, I mentioned that reinforcement learning can be used in conjunction with neural networks, and commonly is used in conjunction with neural networks. I wouldn't be surprised if there aren't other tools that you can use in conjunction with reinforcement learning. And so.
Hi, Dr. Hull. Thank you so much for the amazing presentation. I actually have 2 questions. One is related to traditional statistical methods. As you mentioned house price prediction a couple of times, I was wondering, since house price prediction or this kind of spatial correlation predictions involve a lot of more refined, I would say, traditional statistical methods like Kriging and co-Kriging based on covariances and correlation matrices that have been used quite a lot of times on these spatial correlation related problems. So how does machine learning take into account the spatial correlation or the covariance matrices related to these problems into the predictions?
Okay. In a sense, well, I mean, if we're talking about neural networks, it kind of all comes out in the wash as far as the weights and so on are concerned. But you know, I think, you know, I'll broaden your question a little bit. I mean, what, you know, if you're a statistician, then when you do something like linear regression, you want the independent variables to be uncorrelated and you know, be truly independent. And in theory, you should never do a linear regression unless that's true. Of course, in practice, you know, you don't want variables to be too highly correlated, but you can sort of shrug your shoulders if there's just a little bit of correlation. Now, when we get into machine learning, we actually have various tools to deal with correlated variables. And, you know, so that you could almost say some of these tools are extensions of things like linear regression, and they can also be used with neural networks. So basically, you know, in a model, what is the problem when you have two highly correlated variables? For example, if you're predicting a house price, you might have, you know, the square footage of the first floor and the square footage of the basement or something like that. And those are obviously highly correlated.
Exactly.
Well, yeah, and the problem is then that, you know, the sort of model you'll be overfitting, essentially. You know, the sort of model you come up with, you know, if could have, you know, a big positive coefficient on one of those variables and a big negative coefficient on the other, just because it's somewhat arbitrary, you know, just very fine points. So there are, you know, there are methods that are used called regularization methods that are designed to avoid that. And I haven't had a chance to talk about those in any detail. But basically what regularization tries to do, whether we're talking about neural networks or regression, is to simplify the model. So essentially we might kick out one of those two variables. You know, we don't need the square footage of the basement if we've got the square footage of the first floor. And you know, regularization is going to determine that. So you know, I think one of the differences between statistics and machine learning is that we don't worry about initially having correlated variables in machine learning, because we're going to go through this process known as regularization.
All right.
To simplify the model and kick out
that
variables we don't need. And, you know, this is all part of the sort of whole process of simplifying the model. So we haven't had a chance to talk about that, but regularization is a sort of big topic in machine learning.
That actually makes a lot of sense, actually. Thank you very much for your answer. I would like to ask you a second question, which is more related to finance. These days, since a lot of people are getting interested in crypto trading or becoming investors and traders, and there is some sort of time series data involved, and a lot of people are even trying to get the APIs of these stock trading or crypto trading apps to build machine learning models or some sort of trading bots. So when there is some stock related time series data involved, what sort of machine learning models would you recommend to be best for this sort of predictions? Would you recommend LSTMs, or would you recommend something other than that?
I think, you know, LSTMs, which, you know, I think it's definitely, you know, when you're predicting stock prices or cryptocurrency prices or whatever it is, I mean, obviously the time sequence of your data is very important. So it's not just it's not just a simple neural network where you can jumble up all your data and expect to get the same answer. So therefore, you know, you could use neural networks, but you want to think in terms of a recurrent neural network, which is where you're relating one day to the previous day, or as you say, LSTMs. The nice thing about LSTMs is you're looking back through time and you're saying, what of my previous observations is most important? I can forget about observations from 5 days ago, but maybe not from 6 days ago, things like that. And as I mentioned, machine learning is being used by, hedge funds and asset managers to a great extent. And this is the sort of thing they do. As what we've traditionally taught in finance is that markets are efficient and, you can't make money by analyzing historical data. But it turns out you can. You may have heard of this company, Renaissance Technologies, which is a hedge fund, which has been incredibly successful, run by mathematicians. In fact, run by machine learning experts. And, the original founder, Jim Simons, was not really, I don't think he was a machine learning expert, but the two people who are running it now are definitely machine learning experts. But basically, Renaissance Technologies is a company that's run by mathematicians, not Wall Street types. And it's been just incredibly successful in terms of the returns, 60% per year returns. It's been the most successful hedge fund ever.
Wow.
And why? Because they've been ahead of the market in terms of using machine learning techniques. Essentially, now everybody else is trying to catch up, but they've been doing it for about 20 years. And yeah, they've been looking for, subtle patterns in prices in the market that other people have missed. And all you need is, a 52% chance that this trade will work out and a 48% chance that it won't, to actually develop a trading strategy that will make you money. So, I would say if there is one example that, and I talk a bit about this in the book, if there's one example that illustrates the power of machine learning for the sort of problems you're talking about, it would be Renaissance Technology with its 60% return per year over a very long period of time.
That's amazing. Thank you. Thank you so much.
So you might want to read up a little bit on that. Actually, there's a really good book that's been written about Renaissance Technologies, which, oh geez, I can't find it. But if you Google, which, of course, the other thing about Renaissance Technologies, of course, is they recognized that if they write a paper about all of this and tell everybody about what they're doing, then it'll no longer work. So it's an incredibly secretive company. So, you find this book that's been written about them doesn't really give away any trade secrets, but it's still a very interesting book nevertheless. Zuckerberg is the author of the book, I believe.
Thank you.
Actually, we have 10 minutes left in the event. So we have one last question from the chat section, and then we will leave the last 5 minutes for you, Dr. Hall, to say your last thoughts. So the last question is, in your opinion, what is the most interesting application of machine learning in finance? And in the future, what do you think is going to be the main application of machine learning in finance?
Difficult to choose between all the different applications to say which is the most important application. I mentioned this business of handling exotic derivatives. I think it's an interesting application. I think hedging is an interesting application. I think, doing these big trades and bleeding them into the market and determining the best strategy for bleeding them out. I think that's an important application. And then we've got all the applications along the Renaissance Technologies. So, I'm sort of, I think, new applications are coming along all the time. I think, handling loan applications using machine learning, that's a very important, application in finance. So I think the answer to your question is there are many applications. It depends which part of finance you work in. And I think as time goes by, we'll see many more. You know, it's going to permeate all aspects of not just finance, but marketing and, you know, other areas of business.
So actually we can take another extra question if there is. Yeah, someone is asking, how can we get your book?
Well, go to my website, which you won't find it difficult to go to my website. If you just Google John Hull, you'll get to my website. If you haven't been able to write the website address down, and that tells you how to buy it. As a matter of fact, you know, what I did with this book, I meant to mention, I mean, I actually self-published it with Amazon. Amazon has a system for self-publishing books. And the reason is that it's just, you know, my other 3 books have all done really well, and they've all been with traditional publishers, but dealing with a traditional publisher is a pain in the neck. And it typically, you know, you make a proposal, they send it out for review, they think about it for a long time. You know, there's about an 18-month gap between proposing a book and it actually appearing. And that's ridiculous in this environment. I wanted to get my book out quickly. And, you know, I've been really pleased with how this self-publishing, and you don't need to charge as much for the book when it's self-published because you're cutting out the middleman. You know, so basically what you'll find on my website is the Amazon address to go to buy the book, and it's, you know, it's available in print and online. So you can buy the online version or the print version. Perfect. Preference.
So don't forget to check his website.
Yeah, and as I say, there's lots of stuff that goes with the book on my website that you might find
definitely. Yeah. Any other questions, or I would leave the word to Dr.
Sorry, can I ask about the chess? Like, because you're saying that about the chess that in the algorithms which are most advanced, they just give this game to, like,
just give
the machine. Yes, we give them a rule and machine plays with it with itself. But I know that, for example, I think the players, like human players, they learn sometimes by like analyzing some previous games and like putting them in specific positions, and then, okay, well, if I'm in this position, I have to probably do this. It's better to do this. But you think in this advanced algorithms of machine learning, they don't really do that?
Or yeah, I mean, when I say play against yourself, they play against themselves maybe millions of times. So they see many, many different positions and learn from them. And, you know, I mean, this trick, you know, we've looked at some fairly basic, you know, with the game of NIM, we've looked at a fairly basic sort of reinforcement learning application. The applications, you know, the guys at Google who have been programming AlphaZero, they, you know, they'll use various tricks that we haven't talked about. But yeah, it's okay. If the best, Magnus Carlsen, as you may know, is the best human chess player at the moment, the world champion. And his rating, his chess rating, I think is about 2,850, something like that. So what do you think AlphaZero's chess rating is? It's about 3,600. Okay, it's way, way above any human being. So, and it's actually, it's, you know, it's really sort of interesting to sort of compare the games played by AlphaZero with the games played by the top human players. I mean, AlphaZero tends to be fairly aggressive, you know, pushing on pawns and attacking the, you know, the king in ways that human players often wouldn't do. You know, so you know, you could, you know, if you Google that, you'll get a lot of information about it.
Okay, thank you.
So I'll leave the last 4 minutes for you, Dr. John, to say your last thoughts.
Well, I don't have a lot of last thoughts, actually. It's it's been a long, normally when I teach, when I teach a 2-hour class to students, I give them a 5-10 minute break in the middle, but we didn't have that today. So I apologize. As I say, it's a lot to take in.
It was actually amazing. Thank you so much.
I enjoy presenting this stuff. I think it's a lot more interesting, to be honest with you, than talking about derivatives and risk management. So thank you all for listening to me, and I hope you found it useful. Have a good rest of the day.
It definitely was. Okay, so thank you for coming, all of you, today. Thank you for joining us, and I hope you liked the event. I'm sure you did. And we'll share this event, like the video, on YouTube. We will send you an email once it's uploaded with the link of it. And yeah, have a great day, and thank you for joining us, and looking forward to see you in next events.
Okay.
Thank you.